let's go through some concepts on the final exam. This is the final exam fall 2020. So here's what we have. We got all these problems. So I want to kind of give you an outline of some of the content because we don't have time to, in class to kind of go through stuff and remind you of things as we go. So I'm going to do it on the video. So let's talk about each one. I'll do probably 2 or 3 videos on this, kind of keep them short. So number 1 is a very typical question where you're given rectangular coordinates and find the volume in triple. And it's a setup only, so you only have to do the integration. So you'll have like volume equals, and you'll have a triple integral that gives you the volume of the solid that it determines. So you need to basically sketch and picture what you're trying to set up and then integrate. So the most difficult part really is to get that picture right, and then you can change to a different coordinate system, and we'll talk about that. So this one I'm going to help sketch the graph and then get to a point where you need to set it up. So what I'm going to do is do a rough sketch below and help you set it up. I want you to stay ahead of me as you do this, but if nothing else, take a look at what I have, and then you'll set up your integral. Oh, and then I have a better picture that I'll copy in just because I don't have time to make it real nice looking on a video. So let's take a look. So I have it copied down here. And so let's see what it's saying. So I'll do a rough sketch and I'll copy in the better one. So I'll do it right in the middle. So just, we'll do it and then I'll erase it and come back, if that makes sense. So let's take a look at this. Find the volume of solid of the first octet, right? So first portion there, outside the cylinder and under the plane. Okay, so this is a cylinder. That's a cylinder radius. So again, rough sketch. Cylinder radius 1, like this. So outside that, and then under the plane. So this plane, x, y, z equals 2, you can sketch, over here like something like this, and you can zero out all the values and then kind of get like this. So it's just a plane like that. And it is in the first octant, so it's actually going to be over here. And then you get a picture. So that's going to come down. That's going to come down and hit at 2. So these values here are going to be 2, 2, and 2. But the cylinder, though, is in here at 1, 1, and 1. So it's going to be this little sliver of space that you're trying to go, and then up to the plane. Again, it's getting looking bad there. Okay, so you got that plane, and then the cylinder's inside. You're going to go up to the plane, and then the base will determine the cylinder. So without making that too messy, let me go ahead and show you the picture I have. Okay, so here's what it's going to look like. And I went ahead and labeled it ahead of time, and we can talk about it as we go. Oops, I meant to cut that. Let's just cut that out of there. And let's paste it up here. Okay, so here's a picture I did a little while ago. And let's talk about it. So here's your cylinder, right? You can see that it's radius 1. So these points right here, this would be a 1, and here as well a 1, and then in the back a 1 as well. And then out here, if you zero out x and z, that becomes a 2 and a 2 and a 2. So we're integrating basically around this portion and then up to the plane. So you got to picture the plane being cut off right there. That's what it's looking like. And so at this stage, I really don't care if you use a computer system and do sketch this. To do the cylinder, you need something that does implicit. But basically, here's the graph. Okay, and then let's talk about the lines. So you have what z equals 0 is the xy plane. So that's the octant thing. So you're being cut off by that whole plane down here. And then you need to determine the equation of this line, which you all could do, right? So you just, this is the line that's cutting it off when z is 0. So when z is 0, you get this line that's coming down, and then it slices off right there. So you'll be out to that line. And then you can solve for it, either x equals or y equals, you can solve for that line. So that's no problem there. Here's a little hint. I changed to cylindrical. You can make that determination. I threw that in there. I didn't erase it. I did change the cylindrical, although you wouldn't have to, although let me show you something here in a second. So the other issue is, then what is the, let's draw this region. Actually, yeah, I'll do it. So draw this region. I was going to have you do it, but it doesn't matter. I'll just draw it. So here, let's draw the region in the other plane. Let's see, make that fit nicely. Not really. That fits pretty good. And so in the xy plane, I do want to move that down so it intersects like that. A little better. You have this. And so then you have this, I'm going to need to shrink that. Okay, I'll make that do right there. Then you have this line over here. So if that's 1, so right about here, you got a line that goes like that. So it's this region right here that you're adding around. Okay, so this right here is what you have for a region that you're adding up around this region. So let's take a look at this. This is what I wanted to talk about. So when you're adding up around this region, if you did rectangular, you got to go like from here up. And you see you're going to have basically two different regions, right? You're going to go from the circle up to the line. And then right here, it's going to be the x-axis up to the line. So you'd have to have region 1 and region 2. However, if you use polar, then you'll be able to go like this. You'll be able to go out. Let's just do it like that. And you can see in polar, you just would have to, you'd be using one region. So now you're going to sweep that out across like that. So you'd be like that. So you're in polar, you'll go from, well, it goes this way, right? So it goes from 0 to pi halves. And then you still got to figure out the equation of that line. So what's the equation of that line? You can make that y equals if you want. And then in polar, you're in. The in value is going to be 0 to pi halves. Okay, and then your z goes from where to where? It goes from the base up to the plane, like that. Okay, so so that's your setup. That's your hint of how to do your triple. So your triple integral, you'll say volume is equal to the triple integral. And then it's going to be dv. And so you can now determine whether you do this in terms of rectangular or cylindrical. Would not recommend polar on this one. There's no reason to, because of it's like in my mind, it's like the boxiness of this, of the plane and even the cylinder. It's not quite a spherical situation. But polar, yes, and then cylindrical is polar because of this circle here. And make sure your indexes make sense. Your outside index has to be what every time? It has to be constant. But I kind of gave you that hint right here. Okay, so that's number one. Number two, and you'll just have to bear with me. I'm going to just copy these down as we go. I didn't have it set up totally ahead of time. So two, if I can make that larger. That looks okay, I guess. This is a pretty straightforward one. This is find local, extreme, and saddle points. So this one, I don't think there's really not much I need to really show you on this one other than you know how to do it, right? You're just going to start taking partials. Partial fx, partial fxx, partial fxy, partial y, partial fyy, and then the mixed partials are equal. Then you calculate your discriminant, right? And you run the second partials test. So, pretty straightforward. Just remember that when you have this derivative, let's see, when you do your partials, you are going to have this as a product. You can do this in terms of the product rule. If you're doing derivatives or partial this and then this, right? But then when you do the partial y with this, that's 0. Right, because there's just one variable in there. You could distribute, but that's not going to help because you still have to do product rule again. So and then when you set things equal to 0, if you have e to the negative x, that's never 0. So that's e to the negative x is always positive, right? So it's this, so it's always a positive value. So that's the other thing. Just it's going to be in there, but it's not really going to change much. And then you run your second partials and see what you get. And if you just line up your values, and then do your test. You do your test for the discriminant. So that should be pretty straightforward on that one. Okay, next one. This one. Again, spend a lot of time working through these. These are a little weird, but definitely worth talking about and going through for evaluating that. You need to use the let me paste this here. For this one, using the Jacobian, calculating the Jacobian and all that. And so we're all on the same page here. Let's do this. I'll tell you what to pick U is for. So this, again, I wish I could talk about this. I probably will if you see this before we do our problem session. I will probably go over this one, or one's very similar, but we're going to set this up a little bit. Let U be y minus x, and let V be y plus x. And then you need to do the transformation. So what you'll do is you'll solve for x and y. So you'll solve for y, and you'll get a half u plus v, and you'll get x is 1/2 v minus u. Okay, then you'll calculate your Jacobian. It looks like this: partial xy over partial uv. And so you do, what that looks like is this. It's partial respect to x, partial respect to y. No, that's not it. Let me back up on that. It's partial x. So you first do partial x respect to u, partial x respect to v, and then partial y. So it looks like this. It's kind of like the determinant sort of thing, or I forget the other name of that thing. So this is what this looks like, and I'm sure you should have seen this and looked it up, but I'm just showing you, kind of save you some time. So you should do partial x respect to u, partial x respect to v, partial y respect to u, partial y respect to v, and then you do the determinant. So partial xu is -1/2. Oops. So it's -1/2. Partial xv is 1/2. Partial yu is 1/2. Partial yv is 1/2. And then you do the determinant of that. So when you calculate the determinant, you get -1/2. You can show that calculation, obviously. So that's what comes in to be your integrating factor. And then you need to do the transformations. So the other big deal here is you are looking at your region, how your region is defined. So, and I'll just show you this part over here. Let's just do 2 of these. So I won't show you the rest of that. I'll just show you this part. So you're doing a transformation on a region, and this is your xy, and this is your uv plane. So you're going from your xy plane, which is given, to your uv plane. So you use this information here. This is your region. Your region's given here. It's that trapezoid given by those endpoints there. So it's 1, 1, 2, 2, like that. And so you get this trapezoid in here, like this. And so that's your initial region, which might be more difficult to integrate, or maybe not, but you still got to do the transformation when you do this substitution. So you need to transform that into the UV plane. So you want to figure out kind of what those lines are and how it transforms. So I'll sketch it, but I need you to write in the what the lines are, what the equations are. So your sketch should come over to here, and it'll be 1, 1, 2. It's going to look like this. Let me make sure I counted right. 1, 2, 1, 2. Yeah, so it's going to look like this. I didn't know I did that wrong. Hold on. I knew my points looked wrong. Hold on a second. Let me just do it like this. I'll just zoom in, make it look here. So it's 1, 1, 2, 2. So it's here, here, and then 1, 2, 1, 2. So it's this little region here. Okay, so I'll blow this up. You can make it bigger in your sketch. Okay, so I want you to verify that that's the transformation. Okay, that's what it'll look like. So this will be, so what you do is you figure out what each point is transformed to. Okay, and then check this out. You don't want to go like this, up like this, because you have 3 different regions. You want to go across, so you only have one region to integrate over. Okay, so you need the equation of these lines. So those are lines, you need the equations of those. And then you're going to integrate from this side to this side. That's what you end up doing. So figure out how these points are transformed given this transformation. And then you do your integration. Okay, so then you say what that is. So you'll integrate over the region R cosine y minus x, y plus x, dA, and then you have your transformation. So this will be, I'll do the easy part. This is cosine u over v, and then this is your integrating factor you put in. Okay, then it's going to be du or dv, right? And how do you integrate that? And then you got to actually do the integration, but that part's usually pretty easy. Okay, so with that, along with what I gave you in the videos, should be plenty to work through the rest of those details. Okay, let's see what else we got. So that's 1, 2, 3. Let's go ahead and stop there. We'll say, so this is all the newer stuff. 4, 5, 6, and 7. This is all on chapter 16. This is the previous chapter. So this is all on vector fields and vector analysis type stuff. It's called vector calculus and all that. So we will so look ahead on that, study some of the stuff on conservative vector fields and a vector field and all that. And then we have the important theorems. We have Green's theorem, Stokes' theorem, and divergence theorem. I tell you how to use each one. Okay, and this is the picture for number 5. So that's Green's theorem. So it's integrating around this, and we'll talk about that. Okay.